Good afternoon, everyone. My name's Jim Kervala, and I'm sorry not to be there in person and to participate in the event with you. But I feel very privileged to be able to just take a few minutes to tell you a little bit about what we're doing at Offworld and how that contributes and adds to the potential of a future beyond our solar system. So I'm going to dive in for about 15 minutes and explain what we're doing and how that might be relevant. And if there are a few minutes for questions after, I'll be happy to participate. So the bottom line from our philosophy is we believe we need an industrial robotic workforce to establish infrastructure in the solar system for transport, for habitation, for building, for shipyards, for any number of things that we need. The vision of what we're doing is that we will have millions of smart robots working interactively, built around a modular platform that enables us to operate within the solar system effectively without the evolutionary incumbents that we've undertaken industrialization on Earth. So we're building an industrial toolkit from the ground up to repeat what we've done on Earth, but do it in space. So, of course, I mean, I don't need to go into this too deeply. I mean, from our philosophy, which I think resonates with many, we want a life insurance policy for the planet. We want to increase our ability to have sustainable life on Earth through maybe space-based solar power and other space architectures. And then, of course, there's nothing like opening up the new frontier to maintain a species edge. So those are our three existential reasonings for underpinning our driving philosophy. So space settlement, or settlement in general, has of course always been hard, and space settlement is no easier. Specifically in the early stages, before we get to self-healing, self-contained starships or settlements, to get from here to there, we've got a hard path. And that path into the frontier leads us into locations and environments without atmosphere, in harsh radiation, difficult supply chain and logistics, variable gravities and the effects on human physiology, and lack of indigenous foods and fauna. So what we need are systems to build all the pieces that we need so that when humans get to a particular point and start engaging, life is a little bit easier. We don't need to send humans out with the old classic imagery that we've got from the 60s and 70s of astronauts holding wrenches floating in space next to some large superstructure. We can send robots to undertake this with a great deal of autonomy and system resilience. And we can't just take the methodology that we've used on Earth for industrialization and transfer that forward. I mean, some of the machines used in construction, mining, and other industrial processes today make me pee my pants with the size of them. And we need to figure out a much better way to do this. And so that, and one of the challenges I think we've had, and I know for myself for pushing this for many decades, is it's really hard to create a business model in space for any space endeavor that is pointing outside of Earth's economic sphere. So unless it's data related, small satellite constellation related at this stage, business model is really tough. So we figured out a way to build a solar system toolkit based on a common modular architecture and platform that we can also serve for terrestrial industrial processes. So we're actually now serving mining, construction, and other sectors on Earth and getting paid for it and using exactly the same modules to go directly into a launch vehicle and then launch out into space. We're building off, of course, existing heritage, but the entire nature and history of robotics today, I think, is an order of magnitude less than the robotics of tomorrow. So we're talking about actually two different industrial spheres here. And the autonomous, advanced, modular robotics that we're talking about are many, many different species undertaking dozens, if not hundreds of different tasks, operating in the thousands or tens of thousands, and able together, like swarms of ants or bees, to build large superstructures, large vehicles, operate electrically with a high degree of autonomy and self-configuration so that they can even change their own systems, operational, physical and software parameters. So here you see some of our universal platform architecture that has basically operations, transport and support robot systems for the mobile units. But with the same modular intelligent Lego kit, if you like, we can also build static structures and support systems. So we have three ambitious goals for this architecture. It's to reduce the cost of industrial operations by an order of magnitude, to establish fully scalable solutions, and terrestrially accelerate the growth of industrial productivity. If we can do that and create a platform play where many ecosystem partners participate and pay for these systems and gain a great deal of economic advantage themselves, then from that perspective we're able to move forward and take the additional resources that come our way and then underwrite the pilot programs that we want to establish in space directly out of our own pocket within the next few years. And those pilot programs will include debris removal, space-based manufacturing, lunar surface operations, structural fabrication and creation, and a number of other pilot projects that will demonstrate in-space settlement and the ability to then construct large structures and superstructures. The design constraints that systems are operating both terrestrially and in space, having no infrastructure around them, operating without humans in the physical loop. We may have teleoperated and augmented reality operators within the digital system, digital loop, to enable reinforcement and machine learning to accelerate. Leave no environmental footprint and utilize no consumables, so that the only real consumable you can think of is effectively energy and parts. And we have a methodology for ensuring that breaks free of Earth's supply chain as well. So our program has ambitious integration requirements to enable all this to occur across machine intelligence, space engineering, robotics, sensing and energy, as well as a number of other factors. So the characteristics of this new generation of robotics is quite specific in order to enable a large-scale platform that can allow for solar system vehicles as well as eventually interstellar vehicles to be established and built. The units themselves need to be small, they need to be adaptable, operating on electric power, a high degree of autonomy, and modular. So by making them small and robust, it means we can keep the cost of these units down to tens of thousands of dollars each. We can have many hundreds of them per deployment, or many thousands. That way, if one fails, it can either be reconfigured through service bots and then down to the last module, the failing module being discarded. And in that way, the entire cost of maintenance and repair becomes much more like a consumable rather than a critical point of failure. By being extremely adaptable and environmentally agnostic, we can operate in a range of temperatures, pressures, gravities, atmospheres, dust, physical loading and radiation environments. Now clearly we're not going to launch some of our robotic systems onto the seabed with exactly the same modules that would operate in the cold trap at the lunar poles or in an asteroid field. There will be a common set of standards and interfaces for the general configuration, and then there will be extensions for advanced and super performing modules that can withstand cryogenic temperatures of 40 Kelvin, for example, for really extreme environments. But for the most part, for general operations on planetary surfaces, and in free space, the standard configuration kit will be able to operate across all those environments. By enabling the robotic systems to operate effectively, independent of any particular consumable energy source or hydrocarbon energy source, we can focus on electric energy as the source. Now, whether we then have different forms of batteries and energy storage, but the mainstay in space will be solar power at various levels for support of operations. We're undertaking an extremely wide campaign at the moment of machine learning based on reinforcement machine learning algorithms and approaches to teach our robots how to operate, how to effectively think, and how to learn, and what are the ways to adapt and improve their learning as we go along. So that every day our systems are operating, we're gathering data, algorithms and strong simulations, reinforcing the positives, eliminating the negatives, and giving us a robust learning environment for these robotic systems. And a high degree of modularity and reconfigurability with a common set of standards and interfaces, which will be released early next year. And the modular system is effectively what we hope will become a solar system standard for decades, if not centuries, going forward. That it will be adaptable and backwardly compatible as we build ever larger systems with ever more configurable units from a wide catalog supported by third parties in an open licensed format. That is one of the keys. When you then have modularity and reconfigurability combined with a high degree of machine intelligence, then you have the opportunity for self-configuring systems. So our ultimate master plan, to put all this into context, is to develop our universal robotics platform, which we're undertaking, to basically become an independent company serving terrestrial industrial markets, which we have clients for already. To use this platform then to establish free space and lunar operations, evolve those free space and lunar operations correspondingly into then asteroidal and Mars operations, and take those fabrication and assembly and manufacturing technologies and capabilities to then enable increasing self-replication of different units, and then ultimately take those units from Earth through to the Moon, building on Mars, into self-replication to the final point where we will use these robot systems to develop their own neuromorphogenic chips for neural nets and machine intelligence processing, completely independent of Earth's supply chain. Now let me just repeat that. Our objective is to build computer chips independent of Earth's supply chain. The reason that may prove to be significant and historic is that these processor chips are effectively the most complex devices we have today. If we can establish the entire manufacturing base to build these or forms of chip, may not be silicon in nature, maybe different varieties in 30 or 50 years' time or whenever, those devices will then, having been fully independent from Earth's supply chain, enable us to have a fully independent economy with resources of the asteroid belt, energy of the sun. We have then a orders of magnitude increase in manufacturing, self-replicating, and expansion technology. It is at that point that we can then start building large-scale systems, if you like, then free-floating colonies, and then even starships and shipyards to proceed forward. And so we have a grand vision. We're starting from humble beginnings right now. We're developing machine tools and robotic systems. We're looking at ways to do lunar and asteroidal rock excavation. We've developed our own plasma, mining and cutting devices, as well as our own microwave systems for preconditioning and rock fragmentation. You may not be But what's happened is we just fired a plasma at this. This was
Jim, you're breaking up real bad.
Basically breaking up.
Yeah.
Yeah, but basically you saw the rock breaking off with plasma, just being able to break it off with a screwdriver afterwards. So these tools use no consumables, but just energy, and we're building these to put these on the end of our robots as a modular system. And we've been undertaking a great deal of machine intelligence testing and developing, where we can use those base algorithms with machines on robot arms to break them. So I'm going to cut through those videos just because the signal is a bit rough. But yeah, we've got a good team. We're still a small team. Kicked off in our first garage and then visited various mining and other construction sites, and of course our bots as we build forward. So that's a little bit of an overview of what we're doing. You can also go to offworld.ai and you can see an introductory video on the front page of our website that gives a little bit of the story as well for a couple of minutes. So with that, thank you very much and happy to answer any questions.
So I'll ask the first question. Can you tell us a little bit about where you are with your, you have some proof of concept prototypes for the rovers and the mobility itself, and where are you with the machine intelligence, I guess, of those devices? Hello, can you hear me, Sam?
Can you repeat? Yeah, if you can repeat that.
Yes, just tell us where you are right now. Are you in proof of concept? Do you have prototypes? Where are you in the development?
So we've been quietly operating for about a year and a half now. We've only the last few months kind of come into public view. We've still got a long way to go. We've got some early development prototypes for robotic systems. We've got some machine intelligence framework, and we're hoping to release the first draft of the standards and interfaces for the modular architecture by first half of next year. So it's still early days, but my objective is that we would be able to do our first lunar prototype missions by 2020 or 21. But our first working prototypes are going to be first quarter next year. So we're building them now, and but it's early days yet. I mean, I'd add to that. I guess the one thing that I find very encouraging about the location or the position we're at is that the company is fully funded by contracts with no investment or dilution brought in yet. So it's all driven by customer contracts. So as an advanced spacefaring company, this is quite a good achievement in itself.
Yes. Did I hear you say that near the end of your talk that you were going to be getting to the point where you were self-replicating these robots would be self-replicating, and how far away is that? How long is that going to be?
Right. So because effectively with the robot architecture, this industrial robotic solar system toolkit, we want to be able to undertake every industrial process that we undertake on Earth. We want to be able to use this toolkit to replicate in a modular fashion. So whether it's excavation, extraction, processing, fabrication, assembly, integration, all of those, let's say, engineering processes to build materials, to create alloys, to then assemble them and form them and then build structures, these systems are intended to be able to do that. So in the same way, along that way, we can then build the modular housings, we can start building some of the plastic components, some of the legs and arms and systems, thrusters, and then go into ever more complex structural components and pieces. And at some point, we will have enough level of fabrication capability in space and enough level of complexity to be able to, say, assemble all of the structural components of these modular robotic systems with only the advanced electronics and processors having to be sent up from Earth. At then some point, these will be able to then build those computer chips as well in space. And so the systems, it's not so much self-replication as in they undertake some sort of mitosis and separate and split into two robots. It's basically more an advanced manufacturing capability at a systems level that they can then manufacture repeat units of themselves. And to the point where those actual chip sets are available, I think we may be able to get there in about somewhere between 30 and 60 years, just from going from a reasonably down-to-earth, non-exponential, non-disruptive, non-bullshit kind of set of assumptions. I think we could look at a 30 to 60 year time frame for that chip replication, assuming the commensurate economic growth to justify all of that development along the way. So we're basically talking about building cities. When you can start building towns and cities on the moon and on Mars and in free space, even if they're small, even if they're only housing 100 people or 1,000 people, I think we'll be at the level where we'll start being able to create the critical mass to send up machine tools and fabrication plants to start building those chips.
Any other questions? Yeah, for manufacturing, chip manufacturing, we may have the silicon out there, but that's extremely, I mean, to go and essentially go from zero to manufacturing a chip, it's quite a bit of ambition, no?
No, I think two things. Going from zero to a chip is not credible, and even trying to look at processing silicon, the amount of chemicals you have to bring up for doping and all the other processes don't necessarily make that route of etching chips with our billion-dollar nano fabs particularly a viable route. I suspect we'll be looking at a much different configuration of chip architecture, based more around neural net processing. So the actual chip manufacture might be much simpler in itself, and what then becomes what adds then the necessary complexity is the learning process. So it may be that these machines the chips will be embedded in the new modules generations in space, and then the machines will have to learn from their parents almost. So
Go ahead.
we're talking about a much simpler chip configuration, but then one that ultimately allows for much more complex behaviors.
At the end of the day, even if it's a chip, you still have a transistor, and you still need a portion of it that you're going to end up having to encase in some type of plastic. What chemicals are you going to use in plastic, or even the etching, as you have also said. So even if it's a different type of chip, even if it's, let's say, developed by neural nets or whatnot, at the end of the day, you're still going to have transistors in there, and you're still going to have to etch it, and that in itself is a little bit quite complicated. So, I wouldn't say anything until you said no BS. Within 60 years, I mean, to get a fab going, a chip development fab like that, I'm just thinking of just basic transistors, just a basic NAND gate.
So again, between now and n number of years, I can't say exactly what the process will be, and I don't disagree with anything you said, but in some ways we were very careful to put a strategic master plan of of the nodes of where we want to go without putting a time scale on it. And all we need to do is go step by step, and not worry. We don't need to worry about step 5 right now. There are many different ways of 3D architecture chips, vacuum nanofets, and all sorts of different configurations that may or may not prove viable for those decades hence. So I'm not disagreeing with you in that sense. It's extremely complex, but I'm talking about a context of that sort of readiness when we've got a thriving in-space economy with thousands or tens of thousands or hundreds of thousands of these robot systems creating structures, settlements, vehicles, and processing in space. So that this is basically an evolution. I mean, I'm talking about an advanced level of industrialization. I don't know when that would be in the decades to come. I'm not too worried about when that will be, and I'm not making any particular claims on when that will occur or how that will occur. I really don't know yet. All I can say is the steps 3 to 5 are more. These are the principles of what we want to go for. We're working on steps 1 and 2 right now.
Okay, Jim, we've got another question.
Hi.
Yes.
I'm just wondering, you alluded to having a terrestrial initial market. Can you tell me something about what that market is? How will these robots be used on Earth?
Yes. So right now we have client engagements in the construction and mining sectors. Literally calling for a reconfiguration of how we've done industry over the last 200 years. So we're now working on building deployments of thousands to tens of thousands of our robots of different species, all with the same configurable architecture, to specifically undertake tunnel building, underground facilities building, mining ore bodies and processing in situ, and then assembly of large structures. What's interesting about the levels of autonomy and machine intelligence, when you separate those from the robotics requirements, the same, if you like, the very similar levels of algorithmic development for your machine learning systems can then be applied to multiple configurations, multiple tasks and duties. So as soon as you get a core set of nets that are able to undertake intelligent operations, and still very much constrained and guided operations, but nonetheless initial intelligent operations to, say, cut a beam or assemble a girder or to go and mine and process, that same learning application can be applied to many different tasks. So we're actually undertaking industrial process tasks for customers now. We're still in the development phase, but we have clients actually funding the development and paying us to develop our technology to do this.
Okay, thank you, Jim. How about a hand for Jim Kervala? Thanks for coming. Thanks for your time today, Jim.